Okay, good morning. Just walking through schedule again. We are here. We know we are here going into Lambda calculus. So we'll have at least 2 lectures on Lambda calculus. We might need Friday for this one. We'll see how today and Wednesday go. Otherwise, of course, we'll do Friday will be a continuation of the office hours. And then after that, we go into functional programming. So the 2 topics naturally go together. Functional programming is designed to map almost perfectly to the Lambda calculus. And then we're getting towards the end of the semester here. In this class, there's not much that goes on here once we get out into the study days. So you've got some programs due and 1 report due. The programs are due technically before you go into the Thanksgiving break. But I'm going to let you guys vote on that. So if you want to push one of those out to where they're due during this study days, then that'll be a class decision. Questions about where we're going? Okay. Let's see here. Let's do, we've got 3 sets of notes. One is the set of notes that I put together in text form. So this is going to be normal, like a textbook kind of notes. We have another set of notes similar to that by someone named Rojas. This one's really excellent. I have a little more background material in mine, but he jumps right in and just shows you Lambda calculus operations, a couple more definitions than I provide. It's a really good resource, I think. And then, of course, the slides that we'll use for the discussion. Okay, there's our outcomes, a fair number of them, each one nice and contained. All right, so we've talked about this before. What's computation? And computation is nothing more than mindless rewriting of terms. So it's a manipulation of symbols, right? So we don't care what the symbols are. All we know is that we have well-defined symbols. We have well-defined rules to manipulate those symbols. And so when we think of computation in the colloquial sense, we always think of we think of it as the application of computation. Oh, it's something where you're multiplying numbers together, or you're trying to balance your bank account, or you're trying to figure out the slope of a curve at a point. Those are applications of computation. The raw computation itself, in the most abstract sense, is just manipulation of symbols, rewriting. And it's called rewriting because you take a particular set of symbols and you modify them, right? You rewrite them. I'm sure you guys have seen these puzzles, like you have 6 toothpicks and they form the letter 4, and you can only move 1 and it forms the letter 3, or whatever the puzzle is. That's what computation is. Just a manipulation, a rewriting. Why are we doing this? The main thing is for functional programming. There are some aspects related to computation. So we've already talked about the nature of computation a lot in this course and the limits of computation. And so this falls in line with that. But in terms of practical value, it helps you understand how functional programming works. And certainly when you're being introduced to functional programming, it helps, because functional programming, the forms of the computations and the syntax are radically different from imperative to object-oriented. I think if you go from imperative to object-oriented, it's not too difficult. If you go from object-oriented to imperative, it's not too difficult, but functional is radically different from both of these. So it helps with that. Now, will you ever do functional programming in your career? Absolutely. That doesn't mean you're going to use a purely functional programming language like Lisp, but all programming languages nowadays support multiple paradigms. Java is moving towards introducing some functional concepts, particularly in terms of how they define actions for GUI events. And languages like Python support all the paradigms, so you can program happily in a functional mode in Python, or you can mix and match the modes depending on what you're doing. So the more you understand about how the functional programming paradigm views computation and performs computation, the more versatile you are as a software developer. And of course, formal systems. I believe that being able to think formally and represent systems formally is a basic skill that will help with your software design as you go through your academic and professional careers. And it's not just being able to formally define things that others have, or be able to parrot back what others have. Whenever you're creating a system, you are, a software system or a software hardware system, you're creating a formal system. And if you're able to establish formal rules for the system early on, it helps in the design. There is a relatively small but vocal community of people who really advocate formal software design. And one of the things that they argue as a benefit is that you can do a lot of design and analysis at any stage in the software development process. You don't technically have to wait for the software to be developed in order to do a test if you can model the software and perform tests on simplified models of the software. Or perform proofs. Okay, so where did this all come from? It's designed, I say devised by Alonzo Church, but there were, as with any large scale effort, there was a bunch of people involved, but Alonzo Church was the main driver. And he was doing this in the 30s, the same time that Turing was doing work on the Turing machine. They were both studying effectively the same thing. What Turing was actually explicitly discussing or exploring was, if we ever invent a computer, what can it do? And you remember from the Turing machine module that we did earlier in the course, it looks a lot like a computer, right? It has tape for memory. It has a read-write head for input-output. It has state. What Church did, because he was well, everyone was a mathematician back then, but Church was a mathematician. He was more interested in the abstract notion of what computations can be expressed. So Turing's thinking, if we had a computer, what could be performed? And Church is not even thinking necessarily about a computer. What are the limits of mathematical notations to express things? They ended up at the same place. There are certain things that are not expressible or not computable. And so that general axiom is, the Church-Turing thesis, and both of those names got attached to it, not because they worked together on the same project, but because they came to the same conclusion from radically different paths. This goes into, if you study the mathematics of the late 19th century, early 20th century, there was really a lot of interesting stuff going on, just like in the world of physics with Einstein's breakthroughs in 1905. There were a lot of interesting mathematical questions going on. Hilbert had his list of, I think, 21 famous problems. Church was doing this development of can we develop a universal abstract system that encompasses all mathematics, and he did through the Lambda calculus. So people are asking interesting questions. Gödel is asking questions like, can everything within a particular system be proven? And he came up with Gödel's incompleteness theorem that said, no, all systems are incomplete. Not everything within a system can be proven. So they all kind of interrelate. So what Church came up with is remarkably elegant in its simplicity, as most formal systems are. Remember, most formal systems, small number of things, small number of operators, and then complexity through iteration. So remarkably elegant, remarkably simplistic system that happens to cover all computations. So small, as I just said, formal system, small number of things, small number of operators. The Lambda calculus basically has one thing. Now there's three forms of it, so we could argue there's three things, but it has the thing called the expression. And expressions break down into three forms: just a variable, or a function, or application. There's only one operator, which is the function. Now, I say only one operator. We are going to end up with three rules for performing these for performing operations. So we could argue there's three operators, of which we'll only need two. So when you first look at this, it's crazy because it's so abstract, it's hard to see how there's any application. So if you're looking at these notes and saying, this is crazy, it's so abstract, I don't see the application, you're right where you're supposed to be. Technically, expressions can be recursively, well, they technically are recursively defined if you notice here. So we have the notion of a variable. We have the notion of a function. How do you know it's a function? It starts with lambda. Lambda, variable name, period, and then an expression. But notice an expression, a function, it contains an expression. Well, how is an expression defined? Well, we have a BNF rule for it here, right? We can replace expression with a variable or a function or application. Application is just one expression followed by another. But each of those can be expanded. Recursion is a big deal in the Lambda calculus. So how do you know when you have an expression what you're looking at? If it literally is just a variable name, it's a variable. If it's lambda variable name dot expression, it's a function. If it's two expressions, one after the other, it's application. And that's always true. Now notice in this case, I have what, expression one and expression two. What if they were both variables? That's application, because it's one expression followed by another. So this is just the structural form. And again, if you turn off your brain and just think about, I am doing mindless rewriting according to these structural forms, then you can actually do the work. And it will have no meaning to you because computation is meaningless. We can start to apply some meaning to it, and we will throughout the lectures. So I want to point out right off the bat, that's the whole definition of the Lambda calculus. Now the rest of this is about what clever things people have done with the Lambda calculus. But that's the whole thing. I mean, we haven't talked about the details of the three rules for performing the function, working with the functions. But that's basically it. Notice there is no such thing as a number. We have to invent numbers using this system. That's how fundamental this system is. Normally we think of, well, sure, the number one was just given to us, right? God said this is the number one. And Lambda calculus backs up and says, no, we don't have to start it there. We can start before that and actually derive or invent the number one within the system. So we're talking super abstract fundamental stuff here. And as you'll see, when we do start to work with numbers, it's a horror show. It's just ugly, but it works. Okay, so the variables, just what you'd expect. We can use any simple variable name, x, y, p, q, whatever. Now we could use words like we do in programming, radius or area or whatever, but we tend not to. We tend just to use x, y, z. Single variable names. How do you know you have a function on your hand? It's lambda variable dot expression, and the variable is actually the input to the function. So if you think about functions with having input and output, then this will help clarify what we're about to do with functions. Right, so if we say lambda x dot exp, which is an expression, we could replace that with lambda x dot f of x. So this could become and then it becomes a little clearer. Oh, that's just a function. That's just another way of writing a function with x as the input variable. We're going to call it the bound variable. Two expressions after another is application. Usually, or I should say the most useful form of that is when expression 1 is a function and expression 2 then is an argument of the function. And then we can say that we're going to apply this function to this argument. If the function was the +1 function and I applied it to 7, I should get 8. Now, technically I can't say that because I don't have numerals or math operators yet, but we're going to invent them. It will work. I'll start out pretending they exist because it's just so much easier, and then we will actually derive them later, and that will justify the pretending. Okay, using that second rule, expression 1 and expression 2, you can see from your history with Backus-Naur forms, if I can replace any expression with expression 1 and expression 2, then I could replace expression 1 with 2 more expressions, right? Or let's say I could replace expression 2 with 2 more expressions, and then I could replace expression 3 with 2 more expressions, right? That's how the Backus-Naur form rules work. So I can create an arbitrarily long sequence of expressions. And then the question is that one expression? Like if I had expression 1, expression 2, expression 3, all the way up to expression n, is that one expression or is it n expressions? And the answer is yes. So when we talk about an expression, it can be a very rubbery term. When we talk about value, it's going to become a very rubbery term. It basically applies to what you need it to apply to at the moment. So here's some expressions. X, just a variable, that's an expression. X followed by Y, that's application, with expression 1 being X, expression 2 being Y. Lambda x, x plus 1, that's a function. And then lambda x, x plus 1, space 7, that's 2 expressions. The first one is lambda x, x plus 1, the function. The second expression is 7. Now again, I'm pretending that numbers exist and I'm pretending that math operators exist. We'll get there. So that last one, lambda x, x plus 1 applied to 7, is actually how we're going to form functions applied to arguments. So that would say, well, in the bottom row here, if lambda x, x plus 1 is a function with x as the input, that's going to be the input, 7. Okay, I'm going to pause here for questions. Is it one of those, oh my God, I don't know enough yet to even ask a question? Who's in that state?
Yes.
Yes.
A little bit, yeah.
Yeah. And again, that's pretty much where you should be. That's okay. But just in terms of, let's talk about just syntax. Does the syntax or does this BNF form, I think technically I should do that, right? Does this BNF form make sense? Let's go there.
Yes.
Okay.
And yeah.
So notice, by the way, we started with BNF forms earlier on in the semester, and we've been able to reuse that several times. You know, they are a fundamental part of how you can describe both programming languages, computations. They're very useful. All right. How about these expressions? Does this make sense? Does, you know, these individual expressions? This is a function because it has the lambda variable dot and then some expression following that. Do these make sense? That's application because it's a It's an expression followed by an expression. Okay, good. So stay there, stay at that level where it's like, okay, that makes sense. And don't try, remember, don't try to put meaning in this, because that's where you're going to get lost. You know, well, this doesn't mean anything. Yeah, that's right. Computation doesn't mean anything. These were just really pure forms of computation. The amazing thing is that, as with any form of computation, you can actually bring it into the applied world. Now, it's such a clunky system, you know, that won't happen in a meaningful way. But it turns out functional programming works exactly like this. In a functional world, you actually do this. In a functional programming language, you actually take a function and then put the argument after the function, and that means apply this function to this argument. Okay, so remember, the symbols don't have any inherent meaning. So, you know, what if I said, here, here's capital R, what does it mean? Well, we don't know. It means different things to different people. In the electrical world, it's resistance. In the physics world, it was a gas constant. PV equals nRT. In geometry, it's probably a radius. So focus on the structure. The actual name of the variable doesn't mean anything. So lambda x dot x is the same as lambda y dot y. Why is that? Because it has the same structure. Lambda x dot x, right? Lambda tells us it's going to be a function. X is the variable, dot, and then the expression is just x. So it's lambda variable dot, then the same variable and nothing else. And you'll notice the structure is the same. Lambda y dot y is lambda variable dot the same variable and nothing else. Lambda q dot q, same thing. So in terms of structure, these are structurally equivalent expressions. And because variables have no meaning, we can swap them in and out as much as we want to or as much as we need to. And there are some minor rules that we will have to follow. But overall, these are the same things. We're going to take advantage of that. Similarly, lambda x plus x, lambda y plus y, lambda z plus z, they're the same thing because the y and the z and the x don't have any meaning. Structurally, what are we saying? Take a variable and add it to itself. Right? They all have that exact same form. Take a variable and add it to itself. And your brain might be screaming, no, wait a minute. If I say int XYZ in a program, those are different things. Yeah, they are, because you're allocating memory space, right? But here, this is pure rewriting. And if I said to you, I want you guys to write down a function where a variable is added to itself, and there's, how many people on this call right now? I don't know. There's 12 of us here. What is the probability that every single one of you would have written x plus x? Some of you might write y plus y or p plus p, right? Was anyone wrong, right? If I said write down a variable added to itself, and you just happen to choose different variable names, who is wrong? Who should I give an F to for that?
Preferably no one.
Right, exactly. Yeah, hopefully nobody. Yeah. So the whole point is it's an arbitrary choice. And if it's an arbitrary choice, then the choice doesn't matter. It's the structure. And this is going to be useful because sometimes we'll find situations where we need to actually change the variable names. Number one, to demonstrate that we've really done something useful. But more importantly, there are situations where you can actually accidentally change the meaning of an expression, even though I'm saying they have no meaning. Let's say change the form of an expression. You can accidentally change the form of an expression if you're careless with, if you're choosing to use X or Y or Z or whatever. And so it is helpful to be able to change the values or change the variable names to avoid that accidental change of form. Now here the form is different. X plus Y, not the same as Y plus Y. Form is different. Why? Because on the Y plus Y form, you're adding a variable to itself, and X plus Y, clearly those are two independent values, independent expressions. They should not relate to each other, but Y plus Y does relate to each other. It's the same thing twice. So that's what I'm talking about. Just you can start to learn to pay attention to the form of these things. This is almost like lexing here, right? I take the x and the y and I say, okay, that's lambda var1 dot var1 plus var2. If I strip away the actual variable names, almost like lexing, and then say lambda var1 plus var1, that's clearly different, right? If I take away the variable names, it's clearly different. One is var1 plus var2 and one is var1 plus var1, meaning different variables. In the larger sense, different expressions. Okay, so again, still pretending we have numbers, still pretending we have math operators. If we say lambda x plus x is a function where x is the input, again, the lambda tells us it's a function. The x tells us what the input variable is going to be. And then the x plus x is the body of the expression, right? It's the body of the function. Similar to what you did in math, right? Y equals x plus x, that would be y equals some function of x. But here's what's weird. When we do y equals x plus x in math, if we do that in math, we are actually establishing a relationship between the x variables and the y variables. We're establishing a relationship between the horizontal axis and the vertical axis on the Cartesian coordinate system. If we do this in terms of programming, that becomes an assignment statement, right? Y equals x plus x. And that actually sets up a binding of the value of whatever x plus x is at that time to the memory location associated with y. So that sets up a binding. We're going to talk about binding in a different way, but notice that when we say lambda x plus x, we don't say like y equals lambda x plus x or anything like that. We just say we're going to apply lambda x plus x to 5. If we did that, the answer would be 5 plus 5 is 10, right? Applying it to 5. So notice what's weird about that is we didn't bind it to anything. All we have is 10, but we don't have y equals 10 or anything like that. It's just 10. And that's a little bit different. This notion of assignment or binding is more or less absent from lambda calculus. We are going to use shorthand notation for things. So if we have a particular expression that's useful to us and it's long and ugly, we might replace it with a mnemonic. And you'll see later. So when we invent, eventually we're going to invent numbers. So once we invent 0, we're going to say this expression, we're just going to use 0 as a shorthand for it. And this expression, we're going to use 1 as a shorthand for it. In this expression, we're going to use plus as a shorthand for it once we start inventing those things. But other than that, there's some similarities here. This lambda x dot x plus x is similar to y equals x plus x in the sense that it's a function that has input. And when you apply it to a number, 12, that's the input, and you're going to get 24. So that part is normal, but that part is familiar. What is not familiar is we didn't bind it to anything. So it's not y equals, it's just, here's a function. We'll talk about binding in a second, I hope, if my notes are right. And what happens here is this, we call this actually the bound variable, because what you're doing is when you take and apply this function to something like 7, then the value of 7 is bound to that x for the duration of the computation. So this is the bound function. So if we look in here, variables are either bound and free. So here I have lambda x plus x. We say x is bound. If you say that x is equal to 7, then every x in that expression has to be equal to 7. That's the binding that occurs. Whereas in the next expression, lambda x plus y, x is bound, but y is free. Why is y free? Because it wasn't mentioned up front here. Now, because the generic form is lambda var dot expression, we can put any expression in here, right? So if I said, expression, some kind of expression, am I limited as to what that expression could be? No. There's no limitation on the rules, right? The rule was really clear. That simple BNF form that we had earlier. And because there's no limit, this could be actually another expression. But it gets confusing. Oh, wait, this X and that's an X. Maybe we could make that a Y. And now look at what's happening. We get some interesting scoping rules here. In terms of this, lambda y dot x plus y, just in terms of that little expression, the y is bound, but the x is not bound by this lambda. But because that whole expression occurred inside of this, that x is bound to this lambda, and the y is bound to this lambda, and yes, that can be visually confusing, but the scoping rules are pretty clear. You can borrow from what you learned in scoping from function definition and programming. It's the same thing. You basically have local variables and global variables, right? So here, this first one, lambda y dot y, clearly the y is bound in here, bound to this lambda here. This x is bound by the outer one. If I had, where do I have it? The same thing, a similar thing here. Can you see where the binding occurs? Let's see. This y is bound to that lambda. This x is bound to that one because that whole larger expression occurs inside that lambda x dot whatever. But look at this y on the end. Can you see why it's not bound to anything? The only possible thing it could be bound to is this y, but it's outside the scope of that expression. See the parentheses? So it's outside the scope of that expression. Therefore, that y is not bound to anything. Now, remember when I said earlier that it's convenient to be able to change variable names based on structure so that you don't accidentally change the form? That's what we're going to be avoiding, is if you're not careful, you will accidentally turn what should be a free variable into a bound variable if you're not careful. It's called accidental capture. So, by the way, lambda calculus is ugly, ugly, ugly in terms of just visual clutter. But all we're doing is nailing down how you can determine if something is a bound variable or a free variable inside of the expressions inside of a function. It wouldn't make, by the way, if I said, can I do this? Yeah. Okay, is that an expression, first of all? The variable x, is that an expression? Definition of an expression can be a variable or a function or application. So is it an expression?
Yes, since you're a variable.
Exactly, it's a variable, right? Because that's what the BNF rule says. An expression can be a variable or a function or application. So it's a variable. Now, here's a trick question. I'm telling you it's a trick question. Is it bound or free?
Yes.
Yes. The notion of bound and free actually doesn't really make sense outside of the context of a function. So since I have not done any function definition here, we really cannot ask the question. We only talk about bound and free in the context of functions. So if I were to put a, first of all, is that illegal? function? It's the whole thing. I'm done. Is that a legal function? What makes a function legal? A lambda followed by a variable, followed by a period, followed by an expression. So is it a legal, properly formed function?
It's legal, but it's a little weird.
Yes, it looks weird, doesn't it? Yeah. So is x bound or free in that function?
Free.
Free, right. The only thing that would be bound is if I did y, then the y is bound, or y times x, the y is bound and the x is free. By the way, let's pretend numbers exist. Is that a function? Is that a legal function?
Think so.
Yeah, as long as we're saying that numbers exist, it's legal. Yeah, as long as we're saying numbers exist. And it's the constant function, right? No matter what input you give it, it gives you back the number 5. You could program that, right? Public, int, foo, open curly bracket, or I'm sorry, input, return 5, right? It would be, here, we can program that. Public, int, foo, it takes an integer value of y, and no matter what you do, it just cheerfully ignores the input and returns 5. That's a legal Java function, isn't it?
Yeah.
And that's what this function is doing. It's the lambda calculus form of that. No matter what you give me as input, you're getting 5 back. It is a, hold on. I'm back in the Cartesian coordinate system now. It is the horizontal line at y equals 5, isn't it? In terms of algebra.
Yeah, that's right.
Right. If I want to convert that to algebra, it would look like y equals 5. If you want to make it a function of x, it's 5 times 0, 5 plus 0 times x, right? But it's y equals 5, so it's the horizontal. In terms of algebra, in terms of the lambda calculus, it's just a function that always gives you back 5, no matter what you give, no matter what you put into it. Notice, we'll talk about how to do this, the actual function work in a little bit. Okay, so if you walk through these and be careful with the parentheses, and trust me, parentheses are going to be an issue with this, and it's going to be an issue in Racket, because what did I say? Functional programming languages map directly to the lambda calculus. Lambda calculus, we tend to use a lot of parentheses just to clarify the scoping rules, and the same is true in functional programming languages. So be prepared for a little bit of ugly. Inside here, that's an expression. Well, it's so hard to get this to stop helping. This expression inside there, just based on what you see inside there, is the y bound or free?
Bound.
Bound, and it's bound to that closest lambda y. Inside there, just inside, forget the outer stuff, is that x bound or free? Again, I'm sorry. I'm going to ask. Yeah, let me ask it a different way. Is the x bound by that lambda y? Let's put it that way.
No.
No.
So if I only consider what's going on inside here, the x is not bound to the local function. In terms of programming, that x is kind of like a global variable that got that local function could can access, whereas the y is truly a local variable in terms of programming. Now, is the x bound in the context of the larger expression? Yes. So you all that were saying x is bound, it's bound here, right? That outer lambda x binds the x. So y is only bound here, inside, and the x is bound here at the outer level. This expression, like we've been doing, can get pretty ugly already. So there's a shorthand notation, which is if it's, let's see, how do I want to say this? If I do my lambda x, I can have any expression in there, right? That's true. I'm allowed to do that. But what if this expression happens to be I hate that Microsoft always thinks it knows what you want to copy. What if that expression happens to be that big long thing? That's what we have in that first line. So that expression contains another function, and that function, missing my period, that function contains another function, and you can do this for a long time. And so there's a shorthand mode for that, which is just lambda and then variable, 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 right? And then you can make this a little cleaner. The sequence does matter. The sequence matters. That XYZ that you see here means that X was at the outer level, Y was at the mid level, Z is at the inner level. It's the innermost level. So basically what we started with were functions of one variable. And you say, that Alonzo Church, he didn't know nothing, because everybody knows you can have functions of more than one variable. And there it is. Functions of more than one variable. But it's bound, or this sequence means that X is bound at the highest level, Y is bound at the mid level, Z is bound at the innermost level. If you can't tell from that construction if the X, Y's, and Z's inside that expression, if they're bound or if they're free, if you can't tell, then you have to go back to this kind of a notation, to using the parentheses to expressly say where the bindings occur. Another route, of course, would be to change the variable name. Could be helpful. Okay, so this is all about form. Now, how do we actually make something happen with this? And I think what we're going to do is we're going to get through some basic rewriting skills today, and we'll practice with that. And then on Wednesday, we can cover, okay, let's invent numbers, let's invent addition, let's invent Boolean logic. And hopefully we can cover that Wednesday. If not, we'll go Friday. Okay, so there's 3 rewriting rules. Remember, computation is nothing more than term rewriting. 3 rewriting rules, which I'll name here but not explain just yet. There's the alpha rewriting and the alpha reduction, and the beta reduction and the eta reduction. We're going to ignore the eta reduction. It's basically a claim about structural equivalency of different forms. We're only going to really focus on the alpha reduction and the beta reduction. They're called reductions because you see how ugly these strings can get already, right? That's a fairly ugly thing. And they're called reductions partly because they tend to actually reduce the complexity of the expression that you're dealing with. That's not always true in the short run. We've seen from the Moo puzzle, and we've seen from Turing tape that you can actually, sometimes you have to make things larger and uglier before they get better. But as a general rule, where the reduction is reducing it's reducing the size of it. Now that's technically why it's called reduction. What really you're doing is reducing it to the form where you can no longer perform any computations. So you're reducing it to its lowest energy state, if we apply a physics analogy there, or you're reducing it to its most stable state because there's no more reductions that can be performed. No more rewriting rules can be applied. But the happy thing is, you know, at least in our examples, it does tend to actually literally reduce the length of the string. A alpha reduction, that's the name change that we talked about. You're allowed to replace the variable names as long as you do it everywhere where the variable occurs within the scope of the expression. And the beta reduction applies to, this is where you're actually taking a function and applying it to input. So alpha reduction, as I said, it's nothing about variable names. We can replace lambda x dot x with lambda y dot y. Here we can take lambda x, x plus y, and we can change it to lambda x, x plus s, y, because that plus y or plus s didn't matter. It didn't matter what the name was. Now, again, we have to do it in a meaningful way. I can't do this, right? I can't take lambda x, x plus y, and then change that y to an x, because remember, we have to keep the structure the same. And what's the structure of those two expressions? They're different. X plus y is adding two distinct variables, as we talked about before. X plus x is adding a variable to itself. So if you randomly changed that y to an x, you're changing the structure. And as long as you don't change the structure, you can do whatever name changes you want. And the reason that you're going to do that, as I said, is we can have situations where we have bound and free variables. And if we were to perform an operation just based on the literal variable names that are present on the page, we could accidentally capture a variable. In other words, make a variable bound that should be free. And so how do we avoid that? Change the variable names. Okay, let's do the beta reductions, which are the actual usage of the function. We're applying the function to an argument. Technically, we call the functions operators, and the arguments are operands. After a while, people are so lazy. They don't want to say operator and operand, they just say raters and rands. We probably won't get quite that lazy in the course. Maybe I will. So here's the steps. And again, don't think about it and just rewrite, and life gets really easy. After the fact, you can say, huh, that really worked. But for now, don't think about it. Just follow the rule. The rule says if you have some kind of a function, lambda x, right, lambda variable, and then an expression, followed by expression 2, this is application, right? That's the form of it, is application. And it actually is application where we can use a beta reduction. If the term on the left, right, application is nothing more than expression followed by expression. If the expression on the left is a function, then we can use the beta reduction rule. And it says a very simple thing. Remove this lambda x. Oh gosh, stop helping. Remove this lambda x. And then everywhere you see an x inside this expression, replace it with expression 2. So for example, if we apply lambda x dot x to 7, expression 1 is lambda x dot x, expression 2 is 7. And so what do? We remove the lambda x dot x, lambda x dot, we remove the lambda x dot, and then everywhere we see an x in the expression, we replace it with 7. So we're going to end up with 7. This, by the way, is the identity function, because it always just gives you back what you gave it. So let me go back where I have some more real estate up here. If I do lambda x dot x, and I apply it to 7, first I remove the lambda x dot, which means all I'm left with is x in 7. And then everywhere I see an x, I replace it with a 7. this thing, it's called the identity function because all it does is it gives you what you gave it. Right. This thing says X is the input variable. If you give me an X, I'll give it right back to you. I'm going to do one quick example and then we're going to be done for the day because we're out of time. What if I did that applied to 4? I'm going to get rid of this midterm, which is okay. So we say you get rid of that part, the lambda x period, and everywhere you see an x in this expression, literally just replace it with a 4. You don't think, you just replace it with a 4. So I'm going to stop writing that. If I go from lambda x, x plus x applied to 4, what that means is 4 is the input to that function. So, you know, intuitively, that makes more sense to you, right? Oh, if I have a function or I add x plus x and I say x is equal to 4, what do you say? Oh, it's 4 plus 4 is equal to 8. That's what we're saying here. It's just a notationally different way of saying it. And I'm way over time. So the notes are up. I'll have this lecture up and we'll keep doing beta reductions on Wednesday. You know, practice with a few simple ones like this. Once you get comfortable with the simple ones, we're going to move into developing actual numbers and addition and Booleans and if then else's and things like that. Okay. Thanks.
Professor, I had a quick question about the report.
Yeah.
Did you want us to include like pictures, like examples,
And
or just like descriptions?
no, examples are always the best way to describe something, right? You can describe the process and then give an example of the process.
Okay, thank you.
It's always a good idea.